All right, this lesson is about uncertainties. So due to the fact that any reading you take with a measurement cannot equate to the true value of that dimension, you must account for the uncertainty of that instrument. So for example, in length, we can use meter ruler, vernier caliper, micrometer, screw gauge, but due to the internal, mechanical constraints of it, each of them will have a different uncertainty. Anyway, let's get straight into how to find uncertainty. Now, if you have repeat measurements, there's one formula. You have to use half of the range. Range means maximum minus minimum. Now here you can see how it has been done. Maximum minus minimum and divide by 2. So you have to use half range. You might want to highlight this in your own notes. So that is 2.5 millimeter. So if you're writing the full answer of this reading as a single value, you take the mean and then you put plus or minus the uncertainty. Now here there is some confusion. This is just a bit of a tangent, but this uncertainty has two significant figures. If it was added or subtracted from this 64, you would get 66.5 and 61.5. So 66.5 and 61.5 have three significant figures, but the readings here have two significant figures. So that is normally not acceptable. Like in all the recent past papers, you have to give this one in such a number of significant figures that when you add and subtract it from the main value, the number of significant figures of the main value is unchanged. Here it is the long story that I just said. Number of significant figures in uncertainty cannot be greater than the number of significant figures of measured value. Or rather, you should cut this and say number of significant figures in uncertainty cannot modify the number of significant figures of measured value. So ideally, this should have been given, according to the new rules, this should have been given as 64 plus or minus 3. Because when you add and subtract 3 from this value, the number of significant figures remains at 2. Okay, but now I've thought about this and I put this explanation for why now this is from the official guide, right? Why they put it like this, because a ruler can be read to 0.5 millimeter. So in this case, it's sort of acceptable, but generally you will want to give the number of significant figures of the uncertainty in such a way that it doesn't affect the number of significant figures in the actual value. Anyway, so that's for half range. Sorry, it's for repeated values. Now, if you have a single reading, let's say 66.3 millimeter is a single reading. In that, you find the uncertainty from half of its resolution, right? You might want to highlight this. So now on page 1, I've given a whole list of resolutions and their associated uncertainty. You might see that the uncertainty is exactly half the resolution in each case. You should still know this from unit 1 because they still ask it, okay? Calculating percentage uncertainty, you can find even in a recent paper, I believe June 2022. Okay, so now we know how to find uncertainty for single reading and repeat reading. Now, percentage uncertainty is that uncertainty you got over the measured value into 100. For repeat values, it's now for repeat values, it's uncertainty divided by mean into 100. So this is all about how to convert that uncertainty into a percentage uncertainty. Once you understand that, to compound uncertainties, that means when multiple things are appearing in an equation, like for example, density equals mass over volume, there are two variables. And if the volume is composed of lengths, then it's density equals m divided by L cube. Now there are a couple of variables more. So let's see how to handle those. This is normally in question number 4 of your paper. Right. So there are really only two rules. There's one rule for division multiplication. Let's look at that. That I've put it in big letters here. Total percentage uncertainty is calculated by adding together the percentage uncertainties for the measurements. Now, so that's for multiplication and division. There's an example here, I'll get to that. But for addition and subtraction, you need to add the uncertainty for each measurement. This is different. For addition subtractions, you add the uncertainty. For multiplication and division, you add the percentage uncertainty. Right? It's different. Right. This is the easiest one to understand. Now, let's say student determines the thickness of a pipe wall. So he measures the external diameter and internal diameter. So if he wants to find the difference to get twice the thickness, yes, anyway, because I hope you understand that outer diameter minus inner diameter is 2 times the wall thickness, because that diameter goes through 2 of the walls, right? Anyway, they take the subtraction. For that, you do the main value minus main value to get the main value of the subtracted result. Then to get the uncertainty, you have to add these two together. Uncertainty is always addition of the uncertainties for addition or subtraction measurement. But the main value is treated as normal. 102.8 minus 101.4. Now let's say you are taking a temperature difference from a thermometer. Same thing. The main value, let's say one day it was 18.4 degrees Celsius in the morning, and by afternoon it was 24.3. So it would be 24.3 minus 18.4, just the main value. But the uncertainty of each reading is half a Celsius. So you have to add those two together and you get 1 Celsius for the entire operation. For multiplication and division, they have given a nice example. Now remember, the total percentage uncertainty is the addition of the percentage uncertainties for each measurement. So the first step in this, if you're finding total percentage uncertainty, you need to go for the percentage uncertainty of each thing. Now look at this example. Some fellow has wanted to find the density of a material. It's a cube. He has a cube. He'll measure the mass and he'll measure the length of each side. This is a well-manufactured one. The uncertainty is 0.5 millimeter, telling us that he used a meter ruler. If it was 0.05 millimeter, we would know that he used a vernier caliper. So please know your uncertainty and resolution values. Right. So now the formula is mass divided by volume, which is mass over length cube. Now you have to look at this and see whatever formula you get. First you have to look at it and see whether is it addition, subtraction, or multiplication, division. Right now it's multiplication, division. So we know that we need to add all the percentage uncertainties. So for the main value, you will treat all the values as normal, mass divided by length cube, simple as that. For percentage uncertainty, you need to find this percentage uncertainty of each. Now the rule here is, this is actually mass divided by length into length into length. Length appears 3 times. That's where this power law kind of comes in, right? Since length appears 3 times in this formula, we need to add its percentage uncertainty 3 times. So first, they have calculated 0.5 divided by 24 into 100. Where is that? 2.1%. Now, you keep this percentage uncertainty to a couple of significant figures because you are going to add them together, and the final answer, you will round it. I have, in red color, I have added some commentary to what they have done in the official Edexcel guide, right? So this is 2.1% when you get the percentage uncertainty of the length. You also have to find the percentage uncertainty in the mass. So you look at the mass, look at this. Uncertainty, divide by measured value into 100. That is with the normal rule. Right. So percentage uncertainty in density, you have to put the 2.1% of the length uncertainty 3 times because it appears 3 times in the formula. And the percentage uncertainty of mass is put 1 time because it appears once in the formula. And you get 6.4% as the final thing. Why have they rounded the final percentage uncertainty to 1 significant figure? Let's figure that out. Metin, there's this thing. There's a rule. I've written it down earlier, normally. Now here's the thing. This is where it gets a little hairy. Because Edexcel does not officially state rules for this stuff. But you have to use your judgment here. In most cases, it is better to put the percentage uncertainty to the same number of significant figures as your uncertainty. Now, in all these cases, you can see the uncertainty is given to one significant figure. In this one also, one significant figure. So it now in most cases, you give the percentage uncertainty to the same number of significant figures as the uncertainties you use to calculate it, because that's the same rule we follow for the main data. Now look at this. For the main data, this has 4 significant figures, this has 3 significant figures, but the final answer is given to the lowest number of significant figures. So the same rule should ideally be followed for the uncertainties and the main values, both treated equally. In some questions though, it leaves you with one, like if you look at the data and it's like 4 significant figures, 3 significant figures, and if you were to follow this rule, you end up with a one or two significant figure percentage uncertainty, you might make an exception there. But use your judgment, right? You can see this kind of where a doubt would arise in June 2022 again. Yeah, in the 4th question, you can check that out and look at the mark scheme. I would recommend. Anyway, so that's how they got the final percentage uncertainty, right? And the logic behind the rounding. Yeah. So that's that. Now let's directly get into the examples. So question number 4. Oh, we'll come to this after doing an example. Okay, this is January 2023. Question number 4. So the student wants to ultimately find, I believe, the density of this washer. She records the following measurements for the diameter of the washer. I think this is the diameter of the hole, right? So this is an example of repeat measurements. So we exactly follow the rules of repeat measurements. If you look at the data, you can see that there are no such anomalies, right? Because everything seems close together. Okay, I'm not going to take. I'll make another video explaining how to judge whether data is anomalous in a quantitative way. But for now, the mean value is just add them together, divide by 4. Uncertainty would be maximum 8.56 minus minimum 8.53, divide by 2. That is the uncertainty. If they ask for percentage uncertainty, you do that maximum minus minimum divide by 2 over measured value. That means mean value into 100. Now you can see here that half range calculation is looked for. And here we go. And if you want to find percentage uncertainty, you would take this uncertainty divided by the mean value into 100. Right. Then here we have the student measuring S and D, I think, to figure out like the volume, but let's see. No, area. She calculates a shaded area. That's pi by 4 s square minus d square. I think you will recognize this. This is the outer area minus the inner area, because pi by 4 d square is the area formula. It's same as pi r square, but instead of r, it's d. Anyway, now we have to find the uncertainty in d squared. Only the d squared term, mind you, right? Only d squared. Now, if you look at d squared, you have to look at it and see, am I dealing with a multiplication division or addition subtraction? Obviously, in this case, it's a multiplication because d into d. So d appears twice. So basically, long story short, you take its percentage uncertainty and double it. Why? Because the rule for multiplication is the percentage, total percentage uncertainty is the addition of the percentage uncertainties of the things that are multiplying and dividing, right? It's this part of the this rule, right? Simply that. Now that would be 0.06 over 10.7 into 100 into 2 because D appears twice. Now you have to round that off, ideally to one significant figure. Let's see what the mark scheme says. Cross our fingers. And they've given it to two significant figures. Oh, the uncertainty. Did they ask for uncertainty or percentage uncertainty? Oh, my bad. So once you find the percentage uncertainty, you have to turn it back into, let me show you the mark scheme. So you do the method that we discussed to find the twice the percentage uncertainty. This method, not this fractional uncertainty nonsense. Twice the percentage uncertainty like this. You find the percentage uncertainty of D multiplied by 2 because it appears twice, and into 100 because it's a percentage. This doubling is for the fact that D appears twice. And then you turn it back into this 1.1%. You need to turn it back into a numerical value by multiplying it into 10.7. You get 1.26 millimeter. But considering that, now look at this, 1.26 is your value, but your calculated value is 10.7 squared, which is to 4 significant figures. But you have to look what happens to your answer when you add or subtract the uncertainty. Now, if you find this value, it's 114.49. So, since these values you use to calculate that are given to 4 significant figures, this cannot go beyond 4 significant figures. So, ultimately, we have to make this into 114.5. Now, when you're presenting the answer, you have to do 114.5. Oh, there you can't write plus or minus in the keyboard. So, plus or minus. And then here you have to put the uncertainty. Now, the percentage uncertainty was calculated already using this, right? Uncertainty, percentage uncertainty of D into 2. 1.1%. You apply that to your 114.5 and you get 1.26. Now look at this. If you plus or minus 1.26 from 114.5, you are going to get 5 significant figures. Because see, this one goes up to decimal point of 1 and 1.26 has 2 decimal places. So subtraction would add another decimal place to your upper bound and lower bound. So because of that only, they have taken the 1.26 and made it into 1.3. It should be 1.3. Yeah, 1.3. Only because it will affect the number of significant figures of the upper bound and lower bound otherwise, right? So the rule still applies. The rule about significant figures over here. Now, remember I asked you to make a correction over here. Number of significant figures in uncertainty cannot modify, cut this and cut greater than and put, cannot modify the number of SF of the measured value, right? Oops, sorry. And notice even if you express it, you can also express the this D squared value and express the uncertainty as a percentage, and the number of significant figures of the percentage still matches the number of significant figures of the uncertainty. Now, the next part of this question asks us to find the percentage uncertainty in the area. Now, the area formula is given here. Now, we have to look at this formula the way that we looked at the density formula as well. That was over here. How we looked at, mass divided by length cube. Like that, we have to kind of break this down. So when you look at it, you can see it's a number multiplying into a bracket containing a subtraction. Inside the subtraction, there are these multiplication things. So ideally, we would find the uncertainties of S square and D square, because ultimately, this is a subtraction, we need to add the two uncertainties, right? Now, to find the uncertainties of d square, you have to go through that painful process of finding percentage uncertainty, as we did here, doubling it and reapplying it back to the 10.70 into 10.70. You have to go through that painful process. It is already done. We have this value 114.5 plus or minus 1.3. And then, so for d square, we are set with the uncertainty. Look at the uncertainty of s square. It is also provided to us as 2 millimeter square. Now, here we have a subtraction. So we seem to follow the rule of subtractions, which is uncertainty for each measurement is added to calculate the total uncertainty. So we add the 1.3 for this question with the 2 for this one, and we get the 3.3. That is the uncertainty of s squared minus d squared part only. So let me write this down. Okay. Now s square minus d square is really this, which is given in the question, minus this, which we found in the previous part of the question. So the main value you get as you do normally, 881 minus 114.5. Now you can see this one has 3SF, this one has 4SF. So the final value needs to be given to the lower number of significant figures. So that will be 881 minus 114.5, which gives us 766.5, but I'm going to 766.5. I'm going to leave it like this for now because I'm not ready to give my final answer yet, and I'll explain to you why. There's that pi by 4 guy, we want to do our final rounding after accounting for that anyway. Plus or minus. Now for the uncertainty, what do we do? For addition or subtraction, whatever, we take the uncertainties and we add them together, giving 3.3. Now I'm still okay with my significant figures of the uncertainty because if I add or subtract 3.3 from 766.5, I'm still going to have the same number of SF, and still I have not done the final rounding yet. Right. Now in the formula, it's pi by 4 into this. Now you have to imagine what happens. A pi by 4 comes and multiplies with this whole thing. If you, I'm going to change this into arrow because I'm adding stuff. Right? Yeah. Pi by 4. Now, you don't need to be a math genius to understand that this pi by 4 affects this and affects this also. So you multiply those and see what the case is. Now, pi by 4, that's 3.125 divided by 4 times 766.5 gives me 598.8. Now I'm ready to round to 3SF because this is my final answer. 599. Plus or minus 3.3 into, sorry, just do pi by 4 into 3.3. I get 2.68. Now I'm ready to round. I'm going to put this as 3%. Because, I'm sorry, what I meant. Wait. Since still the percentage uncertainty has not been calculated, better to leave it like this for now, 2.7. Because finally they are asking the percentage uncertainty. So I don't want to lose data before I make that final thing. Let's check with the mark scheme how far it agrees. This was done in class as well. Anyway, addition of uncertainties of this, cool, because it's subtraction. Calculation of uncertainty A using the factor of pi by 4. Now look at this, the same way that we described, of course. Oh, is it 602? Pi by 4 into 766. Wait. Oh, you know what? I'm using, yeah, I'm still getting 599 because I'm not using the full value of pi. I'm using my phone. If you use your calculator, you will get what they're talking about, the 602. Anyway, the pi by 4 also applies to the 3.3, as you can see, giving us the 2.6. Again, I'm not using the full value of pi. That's why I'm getting 2.7. Then the percentage uncertainty is found by taking again this this value over this value into 100. So let's look at another question of the same type, but this time it's a bit more complex. Now in June 2022, you have almost the exact same format, except that here you have to find the reading of the vernier caliper and use it to find percentage uncertainty. And here you have to use the resolution 0.01 being the in millimeters, being the resolution. And from there you figure out the uncertainty and then do uncertainty or measured value into 100. Check the mark scheme for details. But here I'm here to teach you the compounding, right? Here for repeat values, they expect you to find the mean value and the uncertainty. Uncertainty is half range. Now here is a almost carbon copy of the January 2023 paper, except that the formula is little different. Instead of pi by 4 multiplying into both, it's root 3 over 2 s square minus pi by 4 d square. So here again, look at it. They've given a big question to find the uncertainty of A itself. Now, problem. Now you look at it again. This is a subtraction. Inside the subtraction, there are some squarings. So what you need to do is handle the inside layers before you take the main subtraction. So for S, you will do S times S as the main value. For the uncertainty, since it's a square, it's a multiplication. You need to follow the rule, which is the total percentage uncertainty is the addition of the percentage uncertainties of the things multiplying, right? Right now, S is multiplying into S. So the percentage uncertainty of S has to double. So you take 0.02 over 16.83 into 100. That's your percentage uncertainty of S. And you multiply that by 2 to get the percentage uncertainty of S square. But ultimately, we have to convert that percentage uncertainty back into an uncertainty. You will do that by taking that percentage uncertainty of S squared and multiplying that into the main value of S squared. Let me show you in the mark scheme. I'll just load it. One second. Okay, that's fine. Let me show you. Here. You take the percentage uncertainty of S first, multiplied by 2 because it's S squared, S times S, get 0.24. Now you take that value of S squared and multiply it by this percentage to convert it back into an uncertainty. Why are we doing that? Because ultimately you have to realize the bigger operation is a subtraction. So you need to get it back because the rule for subtraction is you have to add the uncertainties, not the percentage uncertainties. So they have converted back to the where is it? Uncertainty. And for d square, same procedure, double because this is d times d of the percentage uncertainty of d. Then apply that back into the value of d square to find the uncertainty. Now, while finding the total uncertainty, you use the factor that they have given also. Just like in the previous question of January 2023. Use pi by 4 into the both of the uncertainties, because ultimately we are adding. Look at this operation here. This one is because it's uncertainty of s squared minus, root 3 over 2 s squared minus pi by 4 d squared. It's a subtraction. In subtraction, we add the uncertainties, and there we go. Even the uncertainties have to be multiplied by these factors though, right? And this is it. Now, if you wanted to again find the percentage uncertainty of area, we would find the area as a numerical value and take this thing and over that numerical value of area into 100. And that is all. Oh, sorry, one more thing. When we are giving the number of significant figures of this final uncertainty, we have to consider the whether we are going to affect the final value of the area. So you would want to calculate that. That's root 3 over 2 s square minus pi by 4 d square. Let me calculate it and get back to you. Okay, using 3.125 as the value of pi, for that area, I got 1.87878729, some value like that. Since d squared is in, if you go back to the data also, this is in 3SF, this is in 4SF, the lowest number. Oh, sorry, they've actually given it, my bad. Anyway, it's 1.88. So you have to look at the uncertainty. Here we go. We are right now over here. This is given to the same number of significant figures that would not modify this 1.88. Look, 2 decimal places. So your uncertainty also ideally they should have given it to 2 decimal places because that would not mess with the value. So here this is a place where Edexcel doesn't follow their own rules. You can gamble 1 mark to that, but the majority of it you must score using the compound uncertainty rules.